Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on graph theory, lecture number 15, in which I will discuss on Aureus and Dirac's theorem for Hamiltonian graphs. Now we describe about Aureus theorem statement. If G is a simple graph with number of vertices n is greater than equal to 3, and if a degree of vertex u plus degree of vertex v greater than equal to n for every pair of non-adjacent vertices u and v, then G is a Hamiltonian graph. Now we prove this. We shall prove the theorem by method of contradiction. Let G be a non-Hamiltonian graph with n number of vertices where n is greater than equal to 3, and it fulfills that degree of vertex u plus degree of vertex v greater than equal to n, where u and v be any two non-adjacent vertices. Let this is number 1. Let us add edges in graph G one by one to get an edge maximal non-Hamiltonian graph G star with same number of vertices n. Here the number of edges have been increased, but number of vertices remains same. The meaning of edge maximal non-Hamiltonian graph G star is that there exist two non-adjacent vertices u and v such that by joining these two vertices U and V by an edge E, then G star plus E becomes a new graph which is a Hamiltonian graph. This Hamiltonian graph will contain one more edge E, then number of edges in the graph G star. G star is non-Hamiltonian graph and G star plus E is a Hamiltonian graph. Since we know that Hamiltonian graph contains a Hamiltonian circuit, therefore Hamiltonian graph G star plus E will contain a Hamiltonian circuit. Let name of the circuit is C, Hamiltonian circuit C. If we delete this edge E from the circuit, then the circuit changes to Hamiltonian path. If we add an edge to the Hamiltonian path, then that Hamiltonian path is converted to a Hamiltonian circuit. And conversely, if we delete one edge from Hamiltonian circuit, we get a Hamiltonian path. Therefore, C minus E, C be the Hamiltonian circuit and E the edge E which was added to edge maximal non-Hamiltonian graph G star. Therefore, C minus E will be a Hamiltonian path. Let this path is denoted by U equal to V1, then V2 dot Vk minus 1, Vk plus 1 dot Vn equal to V. Let this is number 2. Now let S is a set containing I such that Vi vertex is adjacent to vertex U, and T is another set containing I such that Vi vertex is adjacent to vertex B. Now it is clear that degree of vertex U is the number of vertices adjacent to vertex U. That is number of elements in S, means cardinal number of S. We may write this as cardinal number of S. Similarly, degree of vertex V is cardinal number of T. This is cardinal number of T. This is number 3 and this is number 4. Now we retrace the Hamiltonian path U to V as follow. This is U, vertex U equal to V1, then vertex V2, then vertex V3, then vertex V4, then vertex and so on, vertex Vk minus 1, vertex Vk, then vertex dot 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 dot, vertex V n, this is V. If the vertex U is adjacent to vertex Vk, let vertex U is adjacent to vertex Vk. Then V may not be adjacent to Vk minus 1. V cannot be adjacent to Vk minus 1. Otherwise, it will be a Hamiltonian circuit, because Hamiltonian circuit U equal to V1, then V2, then V3, then Vk minus 1, then Vn equal to V, then Vn minus 1. We return back this line, Vn minus 1, then Vn minus 2, then Vk, and then we return back to U, means V1 equal to U. So we start at vertex U, and we go through vertices V2, V3, Vk minus 1, then Vn, then return back Vn minus 1 dot 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 Vk plus 1, then Vk, then we return back through this edge to V1, that is U. And this is a Hamiltonian circuit. Therefore, the graph will be Hamiltonian graph. And this is the graph for G star, because we have deleted the edge joining U and V. Then also this becomes a Hamiltonian graph. Therefore, this edge joining V and Vk minus 1 is not possible. Otherwise, it will be a Hamiltonian graph. We know that if a graph has n vertices, then degree of any vertex may be at most n minus 1. Now let U is adjacent to k number of vertices. Therefore, degree of U equal to k. Let this is number 5 and this is number 6. Here we have seen that V cannot be adjacent to Vk minus 1 or any of these vertices. Therefore, degree of V may be at most n minus 1 minus k. This is number 7. Therefore, degree of U plus degree of V is less than equal to k plus n minus 1 minus k. Implies that degree of U plus degree of V less than equal to n minus 1. This is number 8. In 1, we have assumed that degree of U plus degree of V is greater than equal to n. Therefore, 1 and 8 contradict with each other. Therefore, our assumption that G is a non-Hamiltonian graph is wrong. Hence, for a graph G with n is greater than equal to 3, number of vertices and degree of u plus degree of v greater than equal to n, where u and v are any two non-adjacent vertices, then G is a Hamiltonian graph. Proved. Now we prove Dirac's theorem. Firstly, we state the Dirac's theorem statement. If G is a simple graph with n greater than equal to 3 vertices, and if degree of vertex v is greater than equal to n by 2 for each vertex v, then G, the graph G is Hamiltonian. Now we prove this. Firstly, we take help of Aureus Theorem. We shall take help of Aureus Theorem to prove this theorem. Since given that degree of vertex v is greater than equal to n by 2 for any vertex v of the graph, let u and v be any two vertices of the graph G. Therefore, using 1, we get degree of u is greater than equal to n by 2. This is number 2. And degree of v is greater than equal to n by 2. This is number 3. Adding 2 and 3, we get degree of u plus degree of v greater than equal to n by 2 plus n by 2 implies that degree of u plus degree of v greater than equal to n. This is number 4. From 4, using Aureus theorem, we get that the graph G is Hamiltonian. Proved. Now we solve a problem. Problem is, if G is a simple graph with n vertices and E edge with n greater than equal to 3 and E greater than equal to half n square minus 3n plus 6, then G is Hamiltonian. Now we solve this. If possible, let G is a non-Hamiltonian graph. Then by Aureus theorem, degree of vertex u plus degree of vertex v less than equal to n minus 1, u and v be any two non-adjacent vertices. This is number 1. Let us delete these two vertices u and v. Then it will be a graph H in which number of vertices equal to n minus 2. Firstly, we have n number of vertices and we delete two vertices u and v. Then remaining number of vertices is n minus 2. And number of edges will be, firstly we have number of edges E, and for the delete of vertices u and v, the connecting edge with vertices u and v will be deleted. Therefore, number of remaining edges will be E minus degree of u plus degree of v. Let this is number 2 and this is number 3. Since H contains n minus 2 number of vertices, therefore degree of any vertex of H will be at most n minus 2 minus 1 equal to n minus 3. Therefore, maximum sum of degrees of vertices of H will be, we have n minus 2 number of vertices and one vertex is of at most n minus 3 degree. Therefore, maximum number of degrees of vertices of H will be n minus 2 into n minus 3 equal to n square minus 5n plus 6. This is number 4. Therefore, maximum number of edges of H equal to n square minus 5n plus 6 by 2. Since maximum number of sum of degrees of the vertices of the graph H is n square minus 5n plus 6. Since one edge gives 2 degree, therefore number of edge will be half of this. This is number 5. From 3 and 5 we get E minus degree of U plus degree of V is less than equal to n square minus 5n plus 6 by 2, implies that E is less than equal to, this is less than equal to n minus 1 using 1. So this will be n square minus 5n plus 6 by 2 plus n minus 1 using 1. Implies that E less than equal to n square minus 3n plus 4 by 2. This is number 6. Since given that E is greater than equal to half n square minus 3n plus 6, this is number 7. We rewrite six. E less than equal to n square minus 3n plus 4 by 2, which is less than equal to half n square minus 3n plus 6, implies that E less than equal to half n square minus 3n plus 6. This is number 8. Here we see that E is greater than half n square minus 3n plus 6. Here E is less than this value. Therefore, 7 and 8 contradict with each other. Therefore, our assumption that G is non-Hamiltonian is wrong. Therefore, G is a Hamiltonian graph. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.